Good morning, Laura. I'm going to give everybody a second in case they want to join us. If not, it's just you and me this morning, so. Good morning, Kayla, Hallie, Emma. Good morning, Gus. Just as we go through this, I know I have you all muted right now. But honestly, one of the reasons I chose to introduce the lesson via Zoom is it is a new lesson for me. It's going to be something a little bit, in the end, I found was a little easier. I already did the no reassignment last night. I will tell you right now, I don't remember doing this in Algebra 2. I remember doing it in Algebra 1. So it was something that was new, and I thought might be a little easier if we were able to have at least an exchange in real time, not a 20-second delay. It could be that it's a heck of a lot easier for you than it was initially for me. And hopefully I was able to troubleshoot everything right away for you guys. So with that being said, what we're going to look at is what's called sequences. These are the type of questions where initially when we're younger, they talk about what's the next 3 terms in the list, or can you guess the 4th number in a series of numbers? So that's kind of where this is going. So right away, the first thing that we're going to do is we're going to have a couple definitions here. And the first one is just what a sequence is. And we're going to talk about a set of numbers in a particular order or pattern. And when they talk about each of these, you're going to talk about the terms in the pattern. And that actually is each number of a sequence. We can have sequences that are finite, meaning it's going to have a limit to the list. And then you can have infinite sequences. And that ultimately is just, it's an unlimited number of terms that could end up showing up. When we look at our sequences, the first number is always this a sub 1. So that's always going to be our first term. And our a sub 2 would then be our second in the list. And a sub 3 would be our third term, and so on and so on and so on. And then what they talk about is this a sub n, which is whatever nth term they want us to talk about. So if the list is going to be 15 long and they want us to figure out what the 11th number is, they might talk about that as the nth term. So the other thing that I thought was interesting when I was doing the practice problems and kind of getting an idea of what it meant to have what's called a domain and a range. So when we talk about the domain, it is still our X and our Y when we talk about domain and range. And there's going to be a couple questions that I noticed in the no-re that are actually going to have two graphs, and your domain is still what you would consider your X values. But what this is it's made of natural numbers. And remember that natural numbers have to start with 1, 2, 3, 4. The domain is actually the place in the set. And at first it sounds so silly because I even was like, well, what do you mean by the place? So let's just say I had a set of numbers 2, 4, 6, 8, and it kept going on infinite. We can see that there's this even number pattern, but this position is the first place here. That's the first and the second and the third, obviously the fourth. So this is A sub 1, A sub 2, A sub 3, A sub 4. So those are the places that things appear. When we talk about range, it's made up of real numbers. So it could be anything, decimals, fractions, doesn't matter, could be anything. And that's essentially the outcomes that we're looking at. So it still has that feel of domain and range, but it is this outcome. A lot of times when I was looking at some of the word problems that were getting churned out, or some of the word problems from the textbook, what they're talking about is certain things like the first time I actually did a word problem. The first time Mike plays a video game, he scores 13 points. The second time he scores 26 points. The third time he scores 52 points. If this pattern continues, what would his score be on the 42nd time he played? So the real numbers are those outcome of the individual events, and that's what the domain is, those individual first, second, third, fourth place times that they did something. So that's what we're talking about when we talk about domain and range. So when we go to a graph, just because I saw this when I was, again, doing some of the practice problems, when we talk about, for example, sorry, I'm trying to think about what to write here. So if we have a set of numbers where we're just looking at 3, 6, 9, 12, the domain is 1, 2, 3, 4, because that's how many places are in this set. The range is the actual outcome. It's the 3, 6, 9, 12. So it is different than what we're used to looking at with ordered pairs. The domain is always going to be that whole 1, 2, 3, 4, 5, 6, 7, 8, or however you want to look at it. This will always be what the outcome is. So if I was to look at a graph, on my graph, I would go across the x-axis to 1, but its result would be up 3, over to 2, up 6, over to 3, up. So every time we go to a graph, it's essentially going to be starting at 1, then go to 2, then go to 3. It's the outcome that will tell us if it's going to be what we'll later look at is increasing at an addition, or increasing like we've looked at before with our curves where there's multiplication. This is what's considered a finite sequence because it stopped. If we have on a graph where we've seen already with our parabolas or with our exponential curves, where it just goes on infinitely, especially when we looked at our exponential curves and it started at or excuse me, our rational curves, it had to start at 0. We couldn't have a domain less than 0. It did go on infinitely in one direction, but it had to start with just the natural, not with that 0 start. Well, if we wanted to look at something, a set quite similar, and the only difference is they put that ellipsis at the end, that dot, 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 our domain could be talked about as all natural numbers. So that means that we're starting with 1, 2, 3, 4, 5, 6, but it doesn't stop. So it has that feel like our rational graph would look. Now, our range, again, we're not going to, if you look where this starts here, we don't have any numbers lower than 3. So all of our y values are going to have to be greater than or equal to 3, but then I have to also account for what the pattern is. Well, I'm hoping that we can see that these are all multiples of 3. This was 1 times 3, 2 times 3, 3 times 3, 4 times 3. So you're going to see that set builder notation show up again. Y such that y, and you're actually going to say, is a multiple of, and I'm running out of room, 3, but greater than or equal, oops, to 3. That got jacked up. Greater than or equal to 3. Yeah, that looks horrible. Hopefully yours looks better. Now, I will say, just put a little asterisk or a little note in your notes. On any of the no reassignments, you were not asked. And I looked in the book and I looked at a couple other places. Not a lot of questions are going to ask you to write it this way, because I was wondering why they spent so much time discussing this. They don't ask you to write it, they ask you to understand what it means if you're reading it. So I know we've talked about that in the past, where some of the stuff that they spend a lot of time talking about isn't that you have to know how to write it all the time, it's you have to know what it means if you see it in the directions. But again, this idea of the set is finite, the set is continuous, or infinite, we want to make sure that we understand that the domain is always going to be first place, second place, third place, fourth place, fifth place, and that's what that A sub 1, A sub 2, A sub 3, A sub 4 is. So a lot of this comes down to just being able to read the directions. So after that part, I will tell you things got a lot easier. So I'm going to talk about the first type of sequences right now, because that was just all vocabulary. The first type of sequences you probably saw a lot in Algebra 1. They are called arithmetic sequences, arithmetic. That's where that comes from, arithmetic. And with arithmetic, each term is going to be determined by adding. We're going to add a constant value to the previous term. Now, please remember that just because we're adding doesn't mean that we couldn't add a negative value. So that's something that we have to be very careful with. So even though it might look like subtraction, it's still this idea that we're adding. Now this constant term, this constant value that we add to every previous term, this guy is designated with the letter D, and that is what's called the common difference. And a lot of times the reason is because what you're looking at in a set of numbers is from one value to the next, what's the incremental move between them. So for example, so first I want to point out, because this is something I took note to, when they ask questions, they're not going to tell you, because we're going to also talk about something that's called a geometric sequence, and that's when things have multiplied to move from one value to the next. There isn't this common addition or this common subtraction. So because there's two different kinds of sequences, they won't tell you if it's arithmetic, meaning we're going to add stuff, or if it's geometric. Sometimes they'll just give you these terms that tell you which one you're using. So because it says find the common difference, you know that we're going to have this addition between the terms. Most of you have already beat me to this, so you can already see that what we've done is we've subtracted 3 each time. If it's not that obvious, which I've yet to find with arithmetic when I did all the practice problems, and I actually did a couple of them twice just to make sure there weren't any tricks that I was missing. One of the things that I find is if you took 9 minus 12, you would find that's a minus 3. The next one, if I took 6 minus 9, you would see that minus 3. If I took 3 minus 6, so notice how I'm taking the second term and subtracting the previous, the next one and subtracting the previous, the next one and subtracting the previous. Each time you find this common difference. So it's this idea that that negative 3, that's not going to help, shows up every time. Now, of course, you saw that. Remember, this is because we're adding a negative 3 to every one of them. So when we answer this question, the common difference, D, is negative 3. And that would be how we would answer that question. Now, another question that I could ask from this, and I thought it was interesting that the first couple questions in the no reassignment that I'm giving you are going to be pretty straightforward. It's just testing that vocabulary again. So another question could be, what is a sub 2? Now remember, we talked about that the first value in the set is a sub 1, the second value is a sub 2, the third value is a sub 3, and so on. So when we go to answer this, a sub 2 is the value that's in the second position. So that's 9. And again, it's just being able to identify what the place is and then what the value in that place is. So keep that in mind. All right. So we're talking about if we don't see what the common difference is, that we could subtract the previous number, or again, mental math. The other thing that I found was being able just to identify the place value. All right, so the next example is an infinite sequence, and I know that by the ... And the question is this an arithmetic sequence? All right, so what you want to check is, do we have this common difference? So again, if you can't see the common difference, take the number previous, subtract the one or I should say take the second number, subtract the previous. So -6 minus 5, we're adding that -11. -17 minus a -6, that's still that -11. And we can see, hopefully, that this is -11. So what we would actually do here is say yes. The common difference is -11. And that way it's not just, again, a yes or no answer. We have something to support why. All right. So -4, 12, 28, 42 is this sequence. Arithmetic. And again, you may or may not be able to see this, but 12 minus that -4 says we added 16. Notice the positive 16. 28 minus 12 is 16. So we see a pattern here. But 42 minus 28 is only 14. That messes it up. So the answer is no. There is no common difference, and you have now the support for it. So just kind of like our standardized test that we may have had years ago in elementary school, where can you guess the next term? Sometimes it's not that easy. And so we don't want to sit, and I know I've done this before on standardized tests, where the first level of a pyramid is 1 and the next one's 3 and the next one's 5. How many people are in the 42nd row of this pyramid, and the last thing you want to do is draw dots and have to count them. Or I know the question that I thought of when I heard that example was, how many people are in the pyramid total? Well, that would be difficult to count up all of those. So there's a formula for how to know what's going to end up being that nth term. And a sub n is going to be equal to whatever our first term is, plus our common difference times n minus 1. And we've seen that n minus 1 show up before, even in geometry, when we were talking about the angles in the sum of the angle measures in a triangle. So we know that we have to account for, if we already have one position, what's it going to be for any other position. So our a to the n is that nth term we're looking for. It's that value that we're looking for. A sub 1 is our first value. And D is that common difference, that pattern that we've looked for. And N is the number of that place value that we're looking for. So this nth term, that's ultimately the question we're answering. And then N is that 42nd row of the pyramid. So that's something that we want to definitely use this formula. I will tell you that if you do reference the book pages in your Connect Ed, they go through a very lengthy description of using the point slope formula and linear equations to eventually get to this. I think you can kind of see this is kind of like our points, our slope intercept form. Here's y equals mx plus b. But this is a heck of a lot easier. So I figure we'll just cut to the chase with this one. I want to do an example that I actually found in our no reassignment that does this. So I already kind of have it written up, and I'm going to give you a second. The first one is going to be our arithmetic example. And here's that video game that we were talking about. And I have Mike consistently gets better at a video game every time he plays. He scored 13 the first time, a 21 the second time, a 21 the third time, and so on. How many points will he score his 14th time playing? Now, I'm going to give you a second because I know some of you very well could be copying as we go. I want to assure you that you could solve as you copy as I chitter chatter as usual. And remember, if you miss anything, I will have this uploaded to the YouTube. I'm going to drag it into Google Classroom so that if you miss anything, you absolutely can do what hopefully the other 20 people in your class will be doing later, which is copying. You can pause it. That's what I did. Make sure that you do realize you could do this problem just by finding that pattern and just constantly adding. With arithmetic sequences, it's doable a lot more than the geometric ones because you can just find the pattern and count them out. It's just when it gets to be that situation where it's just too much, you could lose track. So as we do this, the first time is obviously our a sub 1. The second time is our a sub 2. The third time is our a sub 3. So we have, again, our place values. When I look at this pattern, we have 13, then 21, then 29. And we have this thing that's going to go out to the a sub 14 spot. So what I want to do is I want to see, do I have this common difference? Well, 21 minus 13 is 8. And 29 minus 21 is 8. So I can see that D is going to be 8. So I am going to use my formula for A sub n equals A sub 1 plus D times n minus 1. So I know that the common difference is 8. I found that A sub 1, it's where this pattern started, was at 13. And I also know that I'm looking for that 14th position. So when I plug all of this in, I start with 13 plus 8 times 14 minus 1. And we end up in that 14th position. His score will be 117. So 117 will be his score on the 14th time. And that's it. So I will say that after doing a couple of these, I found it was actually a lot easier than I anticipated. So I'm bonehead for having never actually, I never got to this in years past, to be quite honest. So I'm not quite sure what I was so worried about that's probably the hardest question that you will find. I took that right off of the no reassignment. So hopefully, if you get to that, I was able to finish the assignment. And again, this was the first time I've done this. I was able to finish the no reassignment last night in just about 20 minutes. So it may take you obviously a little bit longer, but I'm trying to give you a little bit of a heads up on what the questions are and how to answer them as we go. So that is our arithmetic sequence. So obviously we have and I did another example because I actually got a little nervous and I watched Mr. Colahan's video. So you're gonna see, this actually is the arithmetic sequence he gave his class. I did the notes, they're a lot messier because I was trying to keep up. But I'm gonna put this one in yours as well. And it's the same idea of what I took from the no reassignment. All right, so then we have the next kind of sequence. And it is called a geometric sequence. You're gonna see now this is gonna go a little bit faster because it's the same concept, except we're gonna multiply. So a geometric sequence has the exact same idea. Each term is determined. This time by multiplying by a non-zero, which I think I'll agree is kind of interesting. We're not going to multiply by 0 or else it just is gone. So by a non-zero constant. To the previous term, just like we did with our arithmetic. This constant is called the common ratio. Now remember, our multiplication, that could also be multiplying by a fraction. So that's how it might look like division. So again, it's all multiplication, but it would look like division. And I know some of the problems that I practiced had 2/3 coming up a lot. And this is where checking for that common ratio is really important. Is the sequence geometric? So again, you're going to be asked just to look at a set of numbers. And we're going to check, is it a geometric sequence? So we have -2, 6, -18, 54. Now, here is where that practice of the previous value, this time it's the previous value divided, or I should say the second value divided by the previous. So 6 divided by -2. You end up seeing that you have a -3. -18 divided by 6. You get that -3. 54 divided by -18. You get that -3. This is going to come in handy because I told you that the 2/3 came up. I had 3/5 come up. So it's not going to be something where you're going to see a multiplication by 2 or a multiplication by -3. You're going to have those fractions. I will also tell you one of the examples that I had, and I think it's just on scrap paper here somewhere, had decimals. And so I picked up my calculator and I was switching between, here it is, just to kind of give you an idea. I'm going to zoom in real quick so that you can see that this was a geometric sequence that they wanted me to check. And they wanted to know what the next 3 terms were. And the first one was 0.5, and the next one was 0.6, and the next one was 0.7. Now, I get it. Maybe you are able to see that, but instead of me worrying about dealing with fractions, I took the calculator and I did, of course, the first one, 0.6 over 0.5, that was easy. But then when I went here and did 0.72 divided by 0.6, it gives me 1.2. Well, if I have 1.2 and I just want to do this fast, I can go fraction to decimal and it'll change it into obviously that 1 1/5. I can take that 1 1/5 and go fraction to, see those over the ABC button? That'll make it into an improper fraction. And there's your 6/5. So that way it kind of makes it a little bit easier than having to deal with how do I go between decimals and fractions. So this one was one that I purposely left the scrap paper around so that you can kind of check. So when we're looking at our geometric sequence, you are looking to make sure that that common ratio is there. So then when we answer this question, we will simply say yes, common ratio is -3. Of course, you might have to say no because the common ratio isn't. So let's do 8, 16, 24, 32. So it is that sequence. And here again is where that division will come in handy. So here, 16 divided by 8 is 2. 24 divided by 16, well, you can already see that this is going to be 3 over 2. I'm going to stop. You don't even have to check the rest. There's no pattern. So you're done here. Now, I did say that whether it was arithmetic or geometric, we did have what's the next terms. So the minute you see what the pattern is, if you see that it's multiplied by -3, just keep multiplying by -3. Again, some of my scrap work as I practice some of the problems, I'll show you right here. Some of my scrap work was if I knew what A4 was, I could work my way back if I knew what the ratio was. I divided by 3, I divided by 3, I divided by 3. So you could either work back or forward and honestly just work with what the numbers were, and I just wrote them all down. Over here, I saw what the pattern was, and I just kept adding each time to see if I found the pattern. So a lot of it was just scrap work, multiplying or adding, dividing or subtracting. So don't think of this as a major, always having to use formulas or something. A lot of it is just knowing what the pattern is and adding. So if we, again, don't want to just sit and multiply, we do have a formula for what happens the 42nd time again, because that would be just ridiculous. and it's whatever that position is, whatever that value we're looking for, is this time equal to whatever started our pattern, that first term. This time it's going to be multiplied by the common ratio raised to the n minus 1 power. Where again, a to the n is the value of the nth term, pretty much what we're looking for. A sub 1 is our first term. R is our common ratio. Okay, that multiplication that we found. And n is that any natural number that place value we're looking for, that 42nd time that we're looking for. So I said I wanted to be able to do an example, and I'll bring that paper back. Give you a second to copy that one down. And this time, Morgan's going to run half a mile on Monday, 1 mile on Tuesday, 2 miles on Wednesday, assuming that she continues to increase her distance at a constant rate. Again, they keep making sure they put all those stipulations so you know that we're talking about sequences, constant. How many miles will she run on Saturday? And because these are going to be, again, real life situations, this is one of the few times I've actually seen, again, this is a no-read example, where they're going to tell you to round. And so you keep everything to the exact value until that last instance. And I did do a second question, almost identical, and it said round, and you didn't have to. It was a whole number answer anyway, but they do put that in there just in case. So as I babble, I'll let you guys copy for a second. And here's the situation where you don't see your domain and range like we talked about at the very beginning. You see that the first thing is Monday, so that's our A sub 1. The second thing is Tuesday, our A sub 2. Wednesday, A sub 3. So when we are working this out, what we're looking at is Monday was a half a mile. Tuesday was 1 mile. Wednesday was 2. So then we have to worry about Thursday, Friday, Saturday. So here is our A sub 1, A sub 2, A sub 3, A4, A5, A6. And I need to know what those are because remember, that's our N. That's the value we're looking for on Saturday. So I am going to look for my pattern first. I want to know if this is a common difference or a common ratio. So when I see that 1 minus a half is a half, 2 minus 1 is 1, I can see that arithmetic is not the pattern. So that's something to consider, that you can test it for arithmetic, and if it doesn't work, test it for geometric and see if it works. So if I took 1 divided by 1/2, I can see that that actually is a 2. And if I take 2 divided by 1, I get 2. So my division works. So what we're looking at is that my common ratio is 2. We see that our A sub 1 was 1/2. That's our first term. And we can see that what we're looking for is Saturday, which is our 6th position. So we're going to use our formula. What is she, how many miles is she actually going to run on that 6th day? If what she started with and the pattern she used are those values. So we have 1/2 times 2 raised to the 6 minus 1. So it's 1/2 times 2 to the 5th. So it's half of 32. So on Saturday, A sub 6, Morgan's going to put in 16 miles on Saturday, which I am certain if any of you do any kind of running, I'm not sure if we're going to increase that fast, but that's what the pattern says should happen. So the only other thing I'm going to show you is a couple examples, and I mean show you as in just put them up here and then we are done. I wrote down some examples from actually your no reassignment as I was working. And it does say, given that A sub 5 is 6 and the common ratio is -3, it wants us to find A sub 9. So here's an example of, there's no formula. There's nothing. If 6 was 5, I figured out that the next one, by multiplying by -3, is -18. Well, there's the A sub 6. -18 times -3 is 54. There's our A sub 7. 54 times -3. Notice how I'm taking the previous, that term, and multiplying it again, is -162. Well, -162. And all I'm doing is following the pattern. So again, it's just a matter of multiplying and honestly, at times, maybe writing them out. So you're going to have a couple questions just like that. The following sequence is arithmetic. So now they're telling you flat out, find the missing terms. Well, I scratched out my work because I wanted to make sure, and I'm going to be very upfront with you, I wanted to make sure that I was doing it correctly. Like I wasn't just, I don't know, thinking I knew better. And underneath here, I had that I took my -9 and I subtracted 7 because I wanted to know what the difference was between these two. And if the pattern is arithmetic and it's supposed to stay the same, my increment should be divided evenly. So there's 16 spaces between these. And I showed it because I thought that would help with the notes. And I said, well, it had to be divided because it had to happen 1, 2, 3, 4 times to get to 7. So I divided it by 4. And I found that the increment was 4. And I plugged all the numbers in and I pushed submit and it said try again. And I'm like, what did I do wrong? So I pushed get help. And it took me through that step-by-step process. So notice what the step-by-step process told me to do. It said, here's that term that was at the end of this sequence. Here's where we started. And I knew that I had to account for that common difference 4 times. Well, that's pretty much what I did right here. So that meant whatever I did, I would have to then, to get back here, subtract 4. And to get to the next one, I would add 4. And then I would add 4. And I would add 4. And I would add 4. And that's how we got to the 7. To find out I did everything right, I put 4 here instead of 3. And it was just because I kept thinking about the 4. So when I did put the values in, it was right. And the way I had already thought about it. The point I'm making here, though, is that I used the step-by-step and it really did help. So that's the point I'm trying to make. And because I didn't like that the little square wasn't in green, I went back and tried another one again and it filled. So either way, those do help if you're not doing those step by step. The only other question I had here was, again, same idea. And it does say, follow the geometric sequence. And I did ultimately the same thing that I did with the arithmetic one. I figured whatever I was doing, I had to multiply the same thing 3 times to get there. But I did look at the step by step, and it made a lot of sense to look at it. Here's the end of my sequence. Here was the beginning. Whatever I did, I multiplied itself 3 times. Well, isn't something multiplied together 3 times itself going to be raised to the 3rd power? Had I gone 4 places, that would have been r to the 4th. Had I only moved 2 places to get to 80, r squared. But the same outcome came. Every time I did this, the common ratio was 2. So I was able to multiply by 2 here, multiply by 2, multiply by 2, multiply by 2. So 20, 40, 80, 160. And what you're going to find is, I think, when you do your no reassignment, even if you followed up and did it right now, it will probably be one of the faster ones. So I probably did 5 of, I think, what the 15 questions were right now, if not more. Do any of you guys have any questions on patterns or the formula or the A sub 1s or A sub 2s? I know we don't like to talk to begin with. I just want to make sure if you have any questions that you are able to ask. All right, if not, please note that these notes will go into Google Classroom probably after 11 o'clock. I have to start the honors geometry class here in about 10 minutes. I will also, if you haven't taken a look, I did load the next assignment, the no reassignment. I have that already in no-re, but I will put that in Google Classroom as well. Please continue to hand in your work. I did receive a bunch of them over the weekend that I will grade, and then now that I have a bunch more, you'll notice a lot of those will go in the grade book, and that'll be updated. So if there aren't any other questions, we'll be done for the day. You guys good? All right, thanks guys. Have a good day.
You too, see ya.
See ya.